Okay, this lecture I'm going to go ahead and record. You can watch it on your own. I'm not going to cover it directly in class, in part because we're about a lecture behind on the schedule, and second because this is actually kind of an extra topic, one that's not necessarily needed but reinforces some nice concept. And so it's this principle of the mesh current method. Okay, and I'll explain exactly what that is. And basically it's another way in which we can solve circuits. In other words, we can solve for the voltage across the resistor or the current through a resistor, and to do it in a clever way. It's sort of it's the brother or the sister of the node voltage method. Okay, so again, it's it's somewhat limited in the sense it only works for planar circuits. And what we're going to do here, it's the mesh current. So of course we're going to use Kirchhoff's voltage law. There's a little bit of confusion there. Anyways, with node voltage, we use Kirchhoff's current law. We sum all the currents out of a node. With the mesh current method, we basically the variables are currents, and then we use Kirchhoff's voltage law to give us the equations. Okay, so now what we're going to do with mesh currents, and the only thing that's confusing here is when we talk about mesh currents, these may or may not be the actual current that flows in a wire. Okay, and I'll explain that here in a minute. And so you have to just, in a sense, you have to. There's an abstract concept here. And so you have to kind of understand that these mesh currents are abstract currents that can then be used to give us the real currents flowing in any particular branch. Okay, so what's the idea? The idea is, let's suppose we have a circuit that's like this. What we can do is you can look at that when you draw out this circuit, you can see we have, in essence, these meshes. Here's a mesh, which is basically a non-overlapping loop, of elements that are connected together. So this is a mesh, this is another mesh, here's another mesh, and here's another mesh. But since these guys overlap, this, for example, would not be a mesh. Okay, so now what we do is with each of these meshes, we define what we call a mesh current. So this would be the current that would flow all the way along here, and then a current that would flow along here. And the thing to notice is that the current that actually flows in R6 would be this current I1. No, because I1 splits, right, and goes in three different directions. What we'll think of is the current I1 that flows through R5, VS, and R1. If we think of that part of, think of that current continuing to flow through I6, it's only part of, or R6, it's only part of what flows through R6, but we'll keep I1, and then the part that remains is going to be called I2, you see. And then I2 will have, this current that sort of flows in this mesh, and whatever current, flows through R3, so I2 in this case is not a real current. It's just, it's the difference between, I1 that is a real current flowing through R1 and R5 and the current that flows through R6. That's one way of thinking about it. And then, so we'll have a mesh current here, and then another mesh current here, and the real current that flows, and this current is actually a real current because it's the current that actually flows through R4. But the current that flows through R8 will be I3 minus I2, because I2 flows in this way, or R8. And the current that flows through R3 will be I3 minus I4. I4 is a real current in the sense that it's the current that actually flows through R7, but only, in a sense, part of that current, because it gets split. So part of that flows through R3. And so that's kind of the idea, all right? Let's do some examples. So what we do with mesh current is the first thing you do is you look at the circuit and label all of the meshes. You label the currents in each of the meshes. So what you would do in this circuit is you would say, okay, the current, we're going to think of a mesh current that flows here. That's going to be I1. We're going to think of another mesh current that flows like this, I2, and then another that flows like this, I3. And then we go through and do Kirchhoff's voltage law. So around each of these meshes. So for example, when I go around this mesh, I'm going to go up. So I'm going to sum all the voltages, or in other words, I can do, the voltage in this leg is the same as the voltage in that leg, however you want to think about it. Okay, so when I do that, I go, if I just sum around these voltages, I'll have a minus 40, and then I'll have 2 times I1, and then here I'm going to have 8 times I1 minus I2, because the current that actually flows in this direction is going to be I1, this mesh current minus that mesh current, I2. So I would have 40 plus 2I1 plus 8I1 minus I2 is equal to 0. Okay, that's summing the voltage in this first mesh. In the second mesh, again, I'm going to go in this direction. So I'm going to have 8. And the current now that flows, in this direction, if I want to call plus to minus, that current is going to be I2 minus I1. And you always get these, so you'll have 8 times I2 minus I1. If you do it in a consistent way, there's going to be these symmetries that happen. In the first loop, we had 8 I1 minus I2. In the second, we have 8 I2 minus I1. And then we'll have the voltage drop here, which is going to be plus 6 I2. And then we have the voltage drop here, which is going to be plus 6 I2 minus I3. This is I3 equal to 0. Okay, and then in the third loop, when we go around here, now we're going to have 6 times I3 minus I2 would be the voltage drop. 4 I3, and now I'm dropping, the current or the voltage here is bigger than the voltage there, so I'm dropping there, and I'm going to have, I'll have 6 I3 minus I2 plus 4 I3 plus 20 is equal to 0. Okay, so these are going to be what's called my mesh current. Once I do that, then I can set this all up as a matrix equation. So I would set it up in this way, where I get I1, I2, I3, and the first line here will move the 40 to the other side, and then I'm going to have 2I1 plus 8I1, so 10I1, and then I'll have a minus 8I2, and there's no I3 that appears in that equation. Okay, the second equation, I need to look at all the I1s, so there's an 8I1, and that's it. And then I'm going to have a 8I2 plus 6, so that's 14I2, plus another 6, so that's 20 times I2. And then I look at all the 3's, and I'm going to have a minus 6 I3, and then anything that's constant, there's no constants there, so we have a 0. All right, and then the third equation, I'm going to look for all the I1s. There's no I1s in this equation, so that's a 0. I'm going to sum all the I2s, and so I'm going to get a minus 6 I2 from here. And then I sum all the I3s, so I'm going to have a 6 plus 4 will be a 10 I3. And then the 20 I'm going to move to the other side, minus 20. All right, so then I invert that matrix and I get my mesh currents. And if I wanted to find, for example, in this original circuit, I don't know what's going on with my eraser. Well, can't erase. But if I wanted to find this V0, notice that after I solve this equation down here, then I can say V0 is going to be 8 times I1 minus I2. because it'll be 8 ohms times the current that flows in that direction based on the polarity here. So it'll be the current that flows in that direction will be I1 minus I2. Okay, so I can find that voltage. All right, and the next few slides probably just go through what I just did. So this is, again, we write out these equations given IA, IB, IC. This is exactly what I just went through. And then we form this matrix equation. And if we solve it, these are the answers we get. And now we can go back and find, for example, this V0. All right, so how do we go about solving this equation? So I added a slide here. This is what you would do in Python. So I would open up, what I do on my Mac is I open up a terminal and I type in my terminal. So I do a terminal and then in my terminal, I'll have a thing here. I'll say IPython 3. So I've actually installed IPython 3, and that gives me a prompt that does something like this, okay? And then I would type in, this first line. You could put this all in a script. In the second line, you define the A matrix, the B matrix, and then the currents are just going to be, this would be so I have this equation A times I is equal to B. So the currents, I1, I2, I3, would be A inverse B. And that's this line here. Notice in Python you use an ampersand to multiply arrays together instead of a times. If you do a times, it's going to do like an element by element times instead of a matrix multiplication like you expect. And in MATLAB, and then you can look at each of these by printing them or just typing in I or whatever. And in MATLAB you have something, the syntax is a little bit easier if you're dealing with matrices in Python. Or in MATLAB, and if you leave the semicolon off, it'll just print out the currents there for you. So this is the way you would do it in Python or MATLAB. All right, so let's see. Let's see. Is this the same? This is the same circuit as above. Yep. Okay, so we found everything, and then of course we could actually find, the point I think of this slide is that given IA, IB, and IC before, we can find all of the real currents. So if we want to find I1 here, I1 is just IA, and then if we want to find I3 here, I3 is going to be IA minus IB. So I3 is going to be IA minus IB, and we can find that real current. I2, of course, that's the real current IB here because it flows. And then I4 is because of the polarity, it's going to be IB minus IC. That's here. And then this I5, because we've drawn the arrow different than the arrow with IC, I5 is going to be minus IC. So we can get any of the currents, and of course that means we can get any of the voltages. So once we've solved for the mesh currents, we've found all of the currents and voltages. And the point is that mesh current analysis will give you fewer equations than if you were to just write out the Kirchhoff current law and voltage laws. So it results in something a little bit easier to do. All right, so let's solve this equation. And this one is actually a, this one's a little bit tricky because it has a current source right here in the middle. With we talked about doing super meshes or super nodes with the node voltage method, and here we can do, in a sense, what's called a super mesh, or the mesh essentially. There's a relationship between IA and IC that's specified here. So let's just do this circuit as an example. So if we look at IA and we write the voltages there, we're going to have minus 100 volts as we kind of come up across this thing. And then the 3 ohm is going to be IA. It's going to be 3 times IA minus IB. So we're going to have plus 3 IA minus IB. And then notice that, if we try to sum the voltages, see, we don't know what this voltage is here. So, so what we're going to do, we're summing the voltages, but we have a current source, and we don't know what this voltage is. So what we're going to do is we're going to basically ignore this element here. And we're going to come over and make this super mesh. So our mesh now is going to be basically like this, that doesn't take into account just that current source. And the reason, I'll show you how we can get away with that here in a second, but let's just go ahead and do it. So if we continue, then we're going to have 2 times IC minus IB. So plus 2 IC minus IB. That's a 2. And then, we've got this voltage drop here, plus 50. And then we've got this voltage drop here, which is going to be 4 IC. And then we've got this voltage drop here, which is going to be plus 6 IA equal to 0. Now, when you look at this, so that's one mesh, and then we do this mesh up here in the same way as before. So let's just go ahead and write that mesh. So if we start at this point, we'll have 10 times IB plus 2 times IB minus IC plus 3 IB minus IA. So we're going to have 10 IB plus 2 IB minus IC plus 3 IB minus IA. Okay, and because we started out with 3 unknowns, so normally we would like 3 equations and 3 unknowns. Okay, but because we did the super mesh, we only ended up with 2 equations. But we can use this guy to give us the third equation. So what do we know from this guy? We know that 5 amps has to equal IC minus IA. So we know that IC minus IA is equal to 5. All right, so now we have 3 equations and then 3 unknowns. Again, we form our matrix equation, IA, IB, IC equals. Now let's look at this first equation. We're going to take everything that is multiplied by IA. So there's 3 plus 6 is 9 IA. Now everything multiplying IB. Minus 3 minus 2 is minus 5. And then everything multiplying IC. 2 plus 4 is 6. And then we're going to move the constants. So we have minus 50, minus 100 plus 50 is minus 50. We move it to the other side. We get 50. And this equation, we're going to take everything times IA. So there's a minus 3. And then we've got everything times IB. We've got 10 plus 2 is 12 plus 3 is 15. And then everything multiplying IC, minus 2. And then the constants. And in this case, there's no constants. The constants would come from voltage sources. And now we can do this guy where we have minus IA plus IC is equal to 5. Okay. And now we can solve for IA, IB, and IC. Okay, so that's this notion of a super mesh. And basically, super mesh is when anytime we have a current source, it just says we have a current source that is hooked up here, and we don't know the voltage across that current source. So when we go to do a voltage, when we go to add the voltages around the loop, we can't. But it does set up a relationship between the mesh currents. So that gives us an equation by itself. So we essentially ignore that branch and just do the voltages in in the broader branch that doesn't include, as if we were to disconnect that branch. Okay, so that's this idea of a super mesh. Yep, so this is just written out, what I just talked about. Again, you've got your extra equation here. We've got the two that we talked about. And, you can solve a 3x3 matrix, or you could find IC here, plug it into these two equations, and now you have two equations and two unknowns. So whatever's easiest for you. All right, so we'll do one more. Here's example 1. I don't know if it's one more example or we got another example. Okay, so I'll do 2 examples here. All right, so let's just go back here and do example 1. All right, so we go ahead and label, again, arbitrarily, we label IA. We're always going to label them in a right-hand way. It doesn't matter. These could be different directions. You just have to keep everything consistent. But this will make that matrix that you multiply, it'll make it symmetric. Notice back here that we have a symmetric matrix, meaning, in this case we don't. With the super mesh, we don't get symmetric matrix. But yeah, without super meshes, I guess we get super matrices, or symmetric matrices. All right, just ignore that as rambling. All right, so let's go ahead and solve this thing. We're just going to solve we're just going to sum the voltages around each mesh and get 3 equations and 3 unknowns. But notice in this mesh, we can't, actually do it. So we're basically going to ignore, in this case, we're going to disconnect, and we don't have a mesh, that because this mesh kind of sits by itself, the supernode just gives us a constraint. We'll know exactly what IC is. IC is minus 16 amps. So that'll give us a third equation. So let's go ahead and do it. Let's sum the voltages. We're going to have minus 30 plus 3IA plus 2 IA minus IB plus 6 IA. Okay, so we have minus 30 plus 3IA plus 2 IA minus IB plus 6 IA is equal to 0. Okay, that's summing the voltages around this first mesh. Now we'll sum the voltages around the second mesh. And these will be 2 IB minus IA, because when we're going in this direction, we have a positive to negative if the current goes up. So we'll have 2 IB minus IA plus 8 IB plus 5 IB minus IC plus 4 IB. So we have 2 IB minus IA plus 8 IB plus 5 IB minus IC plus 4 IB is equal to 0. And that is summing the voltages around this mesh. Now on this one, we can't sum the voltages. We'd have 5 IC, but we don't know the voltage across this current source, because the current source, the voltage, the voltage will be whatever this voltage is. And we don't know it because we don't know IC. Well, I guess we do know. We don't know IB, right? But we do know this kind of super mesh result, that IC is equal to minus 16. So we have a third equation. IC is equal to minus 16 amps. So again, we can solve this using IA, IB, IC. We form a matrix equation and type it into MATLAB or Python. So the top equation, we look for everything multiplying IA. 3 plus 2 is 5, plus 6 is 11. Everything multiplying IB, minus 2. Everything multiplying IC, 0. And then we move the 30 to the other side, or the minus 30 to the other side to get a positive 30. Now we come along in this equation, everything multiplying IA, minus 2. That's it. And then everything multiplying B, minus 2. Positive 2 plus 8 is 10. Plus 5 is 15. Plus 4 is 19. And then everything multiplying IC, we would have minus 5. And then any constants, and there aren't any, so it's 0. And then in the sixth one, we would have IC 0, 0, 1 equals minus 16. Okay, and then we would invert this matrix and get IA, IB, and IC. Okay, so in this case, they just plugged in IC equals 16, minus 16, and ended up with two equations and two unknowns. So you can look at, he just took these, we wrote those equations, and he just took the equations that we found, took IC equals 16, plugged those in. Now you get two equations and two unknowns, and that gives you this matrix equation, which when you solve gives IA and IB to be 2 amps and 4 amps. Now we can find any, if we wanted to find the voltage across the 2 ohm resistor, in a plus minus V, and then V would equal to 2 times IA minus IB, which is going to be 2 minus 4, which is minus 4 amps. Okay, so given the mesh currents, we can find anything we want. All right, let's do I have another? Okay, so we'll go ahead and use this particular slide. So this is an example. Now here again, we've got a current source. So the current source forms basically it gives us, we need to do a super mesh because we can't sum the voltages in this loop and around this loop. So what we're going to do is we're going to sum the voltages around this bigger loop, that mesh, and then also the regular mesh. All right, and then we'll use the constraint here, that 2 has to equal IB minus IA to give us our third equation and 3 unknowns. All right, so let's go ahead and sum around the red mesh, and when we do that, we're gonna go in this direction. 10, we'll have minus 10, and then we'll have 2 IA plus 2 IA minus IB, and then we'll come down here and we'll have 2 plus 2 IB minus IC, and that'll give us our first equation. So I'll just write that out. We'll have minus 10, and then we do the 2 ohm resistor on the top times IA plus the 2 ohm resistor coming down the next loop times IA minus IC plus the 2 ohm resistor down the middle, and the current in the positive direction is going to be IB minus IC, and that all has to equal 0. And now we're going to sum the voltages around this mesh. So we'll have 2 IC minus IB plus 2 IB minus, or IC minus IA, and then plus 6, and then plus 1 IC. So let's go ahead and write that. We'll have 2 times IC minus IB plus 2 IB minus, IC minus IA plus 6 plus 1 times IC equal to 0. And now we have 2 equations and 3 unknowns, and we use this this constraint here that IB minus IA has to equal 2. So IB minus IA equals 2. Okay, now we write out IA, IB, IC. So now the first equation. Here we look for everything that multiplies IA. We'll have 2 plus 2 is 4. That's it. And then everything multiplying IB, we have a 2. And everything multiplying IC, a minus 2 and a minus 2. It's a minus 4. And all the constants, we move the minus 10 to the other side. It'll give us a 10. And the second equation, we look for everything multiplying IA. Here's a minus 2. everything multiplying IB minus 2. Then everything multiplying IC. 2 plus 2 is 4, plus 1 is 5. And then we move all the constants to the other side. Here's a constant, so minus 6. And then this equation will have a minus 1 times IA plus 1 IB. Nothing times IC is equal to 2. Okay, then we invert that matrix. We get IA, IB, and IC, and we can do whatever we want. Okay, and I think the previous, this one basically, it took this, they get two equations and two unknowns by taking the third equation and solving for, let's say, IB. They've solved for IB here. Plug it in and then get two equations in IA or IC. They're totally equivalent. You're going to get, by doing this with a 2 by 2, you will get the same answer as if you just do the 3 by 3, solve the 3 by 3 system of equations. All right, so we talked about these two methods. Node voltage, where we sum the currents out of every, we assign nodes, and then our node voltages become the variable of interest, and we sum the currents going out of the nodes. Or mesh current, where we assign currents in the mesh. Again, these are fictitious. The node voltages are fictitious voltages. The mesh currents are fictitious meshes, or currents. And once we set up our fictitious currents, we sum the voltages around the node, solve for our mesh currents, and then we can get everything else that we're interested in. Node voltage is the same. We solve for the node voltages, and everything else falls out. All right, so these are tricks that make solving equations a little bit easier than doing both Kirchhoff's current law and Kirchhoff's voltage law. But doing it, and either one, usually a circuit, will work if one works. A node voltage method works, then the mesh current method will work. And you do have to be careful of these super nodes and super meshes, where if you have in this case, a current source all by itself, or in this case, a voltage source all by itself, you just have to remember how to handle that. It just adds essentially a constraint to your equations, and reduces the number of unknowns, I suppose. You can learn one of these to help, or you can go back to kind of setting up the bigger equations. Okay, so that's these two methods. Which one's better? Well, okay, I guess here node voltage will work even if it's not planar, but mesh currents won't. Which one's easier? Yeah, neither one. And so really it comes down to personal choice or none at all, because you can just go back to the original Kirchhoff's current law, Kirchhoff's voltage law, write things out, and more equations and unknowns than you need. So this is just a way to make life a little bit easier. Oh, yeah, this is an interesting little exercise. So if we wanted to, if you were to say, okay, in this particular circuit, how many, if you're going to do node voltage equations, how many nodes would you have? Okay, so if you were to label this guy as, ground, then you would, you don't necessarily need to use this node as a node voltage because you know that voltage. So you would need to have one here, and you'd need one here. So the number of node voltage equations would be, two equations and two unknowns. With the mesh current, you're going to have three meshes. So there's going to be, you'd have an I1, I2, and I3. Okay, so if we come down, so you need three equations and three unknowns with mesh current. In this particular circuit, so how many nodes do we need? So again, we're going to sum, currents so with the node voltage, you're going to sum the currents. So you're going to have this current, so we need to know, like for example, if this is ground, we know that voltage based on this guy, so we're going to need an equation here. That'll be one equation. We would need an equation there. That will be 2. And then we'll have a current that flows in this direction. And since we know this voltage, we'll know the voltage there, the voltage there. So we only need, again, two node voltages. 2. And again, you've got 3 currents. So you would need 3 mesh currents. Let's see. Let's come down to this circuit here. So again, it's similar. We think of this as ground. We already know this voltage. And then, because we know this voltage, we basically already know that voltage as well, right? So we really need to solve just for this voltage here. So the number of unknowns in the node voltage method would just be 1. And mesh currents, we still need to set up a mesh here, a mesh here, and once we know those 2 currents, we know everything else, right? Because this current is known by this guy minus that guy. So we would need 2 mesh currents. Okay, let's come over to this equation. Now, how many nodes are we going to need to sum the currents at here? So we're going to need, or if we want to do, node voltage. So at this point, we're going to sum, we actually need to know if this is ground, we're going to sum the current here. So we need to know this current, and that current. So that has to be an unknown. Same thing here, that has to be an unknown. And I suppose we would, let's see if we know, that voltage. Nope, we don't know this voltage. So we're going to need 3 node voltage equations here. Now mesh current, you've got your 3 meshes, but one of them is known. So really you can write this in terms of 2 equations, 2 equations and 2 unknowns. Basically we have a super mesh. Okay, same idea down here. How many node voltage equations? We're going to sum all the currents. So we're going to have to sum the currents here. We're going to have to sum the currents there. And here, this is different than that. So we're going to have to sum the currents there. So we're going to need 3 equations for node voltage. And in terms of mesh current, we have a, this guy here introduces a super mesh. So we're going to have one, essentially one unknown, because this will constrain the difference between the 2. And then we have, we know the current that flows essentially in this mesh. And so we have just one. We only need essentially one equation here. And down in this circuit, to sum the currents, we're going to need, we're going to have to sum all the currents there. We'll have to sum all the currents there and there. So we're going to need 3 equations. And then in terms of meshes, we have this upper mesh, and then we're going to have a super mesh. So there would be 2. All right. So hopefully those numbers match what I had. 3, 2, all except for they put 3 meshes here for mesh current. 1, 2, 3. Yeah. Oh, I guess that's true. We have 1 current, 2 current, and a 3rd current. Yeah, we do need 3 equations there. Okay. So again, depending on voltage sources versus current sources, everything here on the left, of course, node voltage is better. Everything on the right, mesh current, might be easier. but you could do either one. Okay, that's all of the slides that I have, and so that's the end of this particular lecture.